Hello fellow problem solvers, so they're going to be doing a problem from the 2008 USAMO problem number 3. This is the United States of America Math Olympiad. So, I invite you to try this nice geometry problem out for a minimum of 20 minutes, ideally an hour to 2 hours, not more than 4 hours. If on the other hand you'd like to go along with us, give this problem a go, like draw the diagram and put your first ideas on paper for the next 10 to 15 minutes. And now without further ado, let us begin. So what do we have here? We have an acute triangle with sides which are different. And we have their midpoints. So let's, draw some. Triangle. And what will we have? We'll have the perpendicular bisectors of AB and AC. A, B, C, D, E, F, G. This is M. What do I call the other ones? M and P. M, and I go N, and I go P. Now these perpendicular bisectors intersect AM. Well, this is just not a very, this is not different enough. Let's have them, let's draw one. This one intersects here, and this one will intersect there. Boom, boom. And call these points D and E, D, E, and then C, E, and B, D meet. Okay, at a point P, what do we need to prove? A and F, P. Okay, so that we need to prove that this point lies really on the circumcircle around with the center diameter AO, like this other point. So I guess the first thing for us to do here would be to see, okay, what are the angles here? Like, let's see, what angle does this problem have? So if you know anything about this, when you connect a vertex with the midpoint of the opposite side, you know these angles aren't well known. You can express them trigonometrically, but overall, not the most well-known thing. So let's maybe look at the problem backwards a bit. Just like see what is it that is happening here with this point F. Where is it? Really, that's my question. And like that's really the first question I have. And now I'm also thinking like maybe we should call these X and alpha minus X because I'm connecting BD and this is X and CE. Mind you, because this is a perpendicular bisector, this is then alpha minus X, so maybe there is something cool-ish about this point. You never know. You never know. You want to make sure. You want to keep these options open. Like you want to think about, even though I don't like this angle X, I don't like it, but I want to see if I can, maybe I can connect it somehow to something. So let's see, what would we have if this point, what is it called? A and F. So if this point lay on that circle, we would have that this angle right here would be 180 minus alpha. Interesting. Will we have any other angles? What other angle conditions will we have? What angle conditions do we have even to begin with? We have this is alpha, alpha minus X, this is beta, gamma, alpha. We have this angle right here is beta, this is gamma. Maybe the thing we need to prove is that PFA is gamma. Now what does that tell us anything interesting? I think now that we've drawn a lousy picture, and this is not an easy problem, and we see, maybe let's see more things before we draw a nicer diagram, just so like we know all the information we need. So I have, this is P, this is this. Okay, let's look at the problem backwards if we've drawn a nicer, a bad diagram that we're going to change now. If this was gamma, if these four were concyclic, what would also hold about this point P? That is the question. Where would it be? What would this angle be? This angle would be equal to this angle, would be equal to this angle right here. Is this angle anything interesting? Do we know anything about point P? Anything that's peculiar? Well, not point P, point F. Why this line? What is it about this intersection? Maybe we know what this angle is. Maybe we can get these two angles. That's difficult. Though, wait a second. I'd get gamma, I'd get beta. Like these two triangles are similar. Maybe if we just like scale everything by 2, I'm curious what happens then. What happens if I have these like perpendiculars that go to here, that meet at O, that they meet AM in these two separate points. And then I really have, then I don't have anything really nice. But this should all be at the same angle. I don't know. So now here's where I invite you to pause for another 20 minutes and draw a better diagram, because that's what we're going to do now, and we're going to erase this thing here. So now that we've drawn a better diagram, I want you to look like I actually paused here for a couple of minutes and actually thought about, whoa, how do I actually go ahead and approach this problem? And here's what I do, mind you. I draw a nice picture, and now I'm looking at, okay, what could hold? Sometimes what's cool in geometry is if you have this at your contest is, have different colors, right? Then you can color different lines differently, and that can also help you potentially in solving the geometry problem. It can help some things like just pop up. Now, what I noticed looking at this picture is I introduced the circumcenter because that is used. Like this is the triangle with the, I need to prove that OFA is 90 is like another equivalent claim to prove. And I thought because these are sort of defined like this, like what happens when I just add the circumcenter of ABC? And for me, the thing I noticed, I wasn't sure, like first I calculated all the angles. And I hope you've done this, because calculating the angles gives you like, especially when you're trying to prove that these 4 points lie in a circle, it gives you like everything you sort of have with these points. And next is noticing stuff, right? What do you notice? And I was looking at everywhere around the picture and I couldn't solve it. And then I noticed that, wait a second. I calculate this is 2x, 90 minus x, 90 minus x. This is x. And then this really PD is the angle bisector of, is the outer angle bisector of, what's it called, FDE. And this triangle is, interesting to me because it's the triangle from which P is from which F is sort of formed. And then I saw, wait a second, this is one angle bisector another, so I have that this angle over here, it's 180 minus 2 alpha. But now, given these two are bisectors, I get that this is 90 minus alpha and 90 minus alpha. Then OF is the internal angle bisector of DFE, right? And now that is pretty cool. And now let's try to solve the problem backwards. I invite you to pause for 2 to 3 minutes and try to see what do you have if you're solving the problem backwards. And the answer is, if you're solving the problem backwards, you have, well, then this angle right here would be alpha, right? The angle DFA would be alpha, and the angle EFA would be 180 minus alpha. But we'd have AFB is 180 minus alpha. This is x. So that means this angle right here would be alpha minus x. And that's also, and what is alpha minus x? It's this angle here. So the point AF, like the line AF, would be symmetric with respect to the angle bisector of BAC, would be this line symmetric to AM with respect to the angle bisector of BAC. So with this in mind, I invite you to pause for another 20 minutes and see if you can push the problem further and put your next ideas out on paper. And now, here's the next step. And from here, there are 2 ways to really go about this. One way is by saying, wait a second, let me see, like I get, when this is 180 minus alpha, and this AFC is also 180 minus alpha, I get a similarity here. I get two things instead of one. Here I need to prove one thing that gives me two things, but here I have two things. And can I use these two things to get the one thing I need? So can I redefine f? Can I define f to be the point in a triangle ABC? So ABC, everything's the same, and call f prime to be the point such that these two, f prime, such that, yes, it should be BC, this is gamma, such that both of these are 180 minus alpha. So there's a unique point such that this is true. And now the thing we need to prove is that when we intersect BF with AM, that we will get a point which is equidistant to A and B. And then that's really the problem that we need to solve. So let me actually draw a somewhat nicer diagram. Actually, it's not too much nicer. So we have midpoint M, B, C, A. And we also know that for this point, we should get that this angle is equal to this angle. So maybe that's the first thing we sort of try to prove, is that this point satisfies that this angle is equal to this one. Call this point f prime. And I think, once we get that, the conclusion immediately follows, because if this is x and this is x, this is alpha minus x. So when we intersect this, alpha minus x, we're done. Because then f is, mind you, then we've shown that this is 180 minus alpha, 180 minus alpha. And then for O, what do we have? We have this is 2 alpha. If we take an O f prime A is going to be 90, and we will be done. So now the crux of the problem is, if I've taken this point f prime, can I prove that this angle is equal to this one? And let's actually call this angle right here x, then this is alpha minus x, then this whole thing is alpha minus x, and this thing is x. Now I have these triangles They are similar. And what am I going to do with that similarity? Well, there are a bunch of things I could do to prove this. The simplest thing to prove here is trigonometry. It's just using trigonometry to get that sine of x over sine of alpha minus x is equal to. Because here what we have, sine of x over sine of alpha minus x, we would have in this triangle, we'd have MC over BM, and we'd have times this over this. So we'd have sine of x over sine of alpha minus x actually would be equal to AB over AC. So we need to prove that if the sines, this is another lemma that we can use, and the lemma is that if you have a triangle, right, and if you have these two angles called Z and gamma and Y, then if the sine of alpha minus Z over sine of Z is equal to sine of this over sine of this is equal to sine of alpha minus Y over sine of Y, that implies Z is equal to Y. That is the lemma that we can use here. And the idea here goes, okay, they are similar. I have, this is equal to, on one hand, let's see how we do this. On one hand, this is BF prime over AF prime. And it's also equal to, on the other hand, sine of x over sine of alpha minus x is equal to AF prime over CF prime. And now, when I multiply them through, I'll get sine of x over sine of alpha minus x squared, when I have this twice, is going to equal to BF prime over CF prime. And now can I get something from their similarity? What do I have from the similarity? I'll have that be F prime, that's opposite x, over A F prime is equal to AB over AC. And also, I'll write this as AF prime over CF prime is also equal to AB over AC. Right, AF prime or CF prime, opposite alpha minus x again is AB over AC. When I multiply these through, I'll get that BF prime over CF prime is in fact equal, this is not equal, I'll get that this is equal to AB over AC, that's AB over AC squared. And now I have that sine of x over sine of alpha minus x, sine of x or sine of alpha minus x is equal to AB over AC. And from here, if I say I can construct, actually let me do it this way. Let me reflect here to get the point x, call this point m prime. And now I have on one hand, this is equal, I have sine of x over, so AB over AC, what is that? That's sine of gamma over sine of beta. Right, when you look at the signs of these two triangles. So sine of x over sine of gamma is sine of alpha minus x over sine of beta. Sine of x over sine of gamma, this is equal to am prime over m prime c, and this thing right here is equal to am prime over m prime b, so m prime c is equal to m prime b. In other words, m prime is in fact the midpoint, and we've then shown that f prime is in fact the point that we've been looking for. Because when we intersect it here, we get that this angle is, like this is the midpoint, the line AM that we had from our problem, and we'll get that this angle is alpha minus x, and this is alpha minus x. So this is equal to this, and analogously also, this is x, this is x, this is equal to that, and we are done with the problem. Another way is just to try to use this lemma directly here. And the thing is, I need this angle to be equal to this one and this one. That one, so it's a perfect place for the lemma. But I don't have these two angles. However, I have this angle, I have this angle, I have this angle, and I have this angle. So what should I use to get the sines of these two angles? This angle or this angle? And the answer is trigonometric Cheva. I know it's not the most beautiful answer, but it's important to also, be able to solve problems like this. What does trig Cheva give me? It gives me the sine of, it gives me this sine, the sine equality, and I know now sine of FCA. So let's do sine of FCA is equal to the sine of alpha minus x. L over FCB, sine of gamma minus alpha minus x. Then we have sine of FBC, sine of beta minus x over sine of x. We have this is equal to sine of the angle FAB over sine of the angle FAC. Right? And now, what are these two things? Well, sine of beta minus x and sine of, sine of gamma minus alpha minus x, we are going to get r is equal to, it's equal to that. It's not very nice. I have x, I have beta. How do I get beta minus x? I think that's not a problem. And let me clear this up. And now I have this situation. I need the sine of beta minus x if this thing right here is x as we've made it here. So how can what is a good way? I can use d to get sine of beta minus x and then use this common thing. But then I'll just get on this over, what's it called? Actually, I could use that. I would get d, I'd get maybe sine of beta minus x would give me sort of dm over, well, let's say we use the sine of this angle because then this one will cancel out here. We'll get some dm over em. It's not too bad, but it's not really the best way. It's not and I have a minus, it's doable, definitely. The only thing is it doable in the way you want to do it, right? So for me, it's like, let me try to do the opposite. If I have this, if I give this angle x, now this is beta minus x, and I'll call this point Q. For those of you that have watched one of my lemmas, this is a famous point in these videos. And now this angle right here is beta. And now what do I know? I know these two triangles are similar. The triangle, this one and this one are similar because this MB is a tangent. And we also know, because now MB squared is MC squared, we know this is alpha minus x. This one is also going to be alpha minus x, because this squared times this times this is equal to this squared and is equal to this squared. So we have this must also MC squared MC must be the tangent to CQA, that circumcircle. And now with that, this angle right here is gamma. And we'll be able to calculate now this is going to be gamma minus alpha minus x. And remember, we've been trying to calculate these signs. Sine of alpha minus x, sine of beta, yada yada. But now look what we have here. We can again use trigonometric Cheva but on this point Q. I think that's the cool, like trigonometric Cheva is just an application of sines. I think here it's just like cooler to like use it again, and we get from here that, so what I need, I'll need sine of alpha, let's do sine of, I'll need the beta minus x at the beginning. So let's do sine of beta minus x over sine of x times sine of alpha minus x over sine of gamma minus alpha minus x times the sine of alpha minus x over the sine of x is equal to 1. And now look what I have. I have alpha minus x, beta, alpha minus x, beta, gamma. These two things are identical. So it must be that sine of the angle FAB over sine of the angle FAC needs to be equal to sine of alpha minus x over sine of x. Now let's call FAC Z. This is alpha minus z. Now just to prove the lemma, we have this. And now what happens when you multiply these through? You'll get sine of z times sine of alpha minus x is equal to sine of x sine of alpha minus z. Now how do you get sine of A times sine of B? Well, you need to use cosines. In fact, you need to use I think you first add, it doesn't matter if you add or subtracted, like you just need to switch the signs. Actually, you need to switch the signs, you need to add. So you need cosine of z plus alpha minus x. And then, because cosine is always positive, the thing that changes is the plus or minus in front of the signs. If I'm not mistaken, then I need to subtract to get cosine of this minus this is alpha minus x minus z is equal to cosine of x plus alpha minus z minus cosine of alpha minus x minus z. These cosine cancels out. I have cosine of A is equal to cosine of B. Under which conditions is this true? I don't expect you to know that. I usually just draw a circle and I see, okay, what do I need to be true? The cosine works. What is the cosine? Like cosine of 30 is supposed to be the bigger one? No, cosine of 30, yeah, cosine is bigger at 30. So it's also it's where x is. That's how you find out. And the x coordinates need to be the same. And that is only true if the sum of two of them is 180 or they're the same thing. If the sum of this and this was 180, that would imply 2 alpha is equal to, actually, their sum would need to be 360. That would imply 2 alpha is 360, alpha is 180. That is absurd. This is an acute angled triangle. And if, then the other thing must hold true, which means that z plus alpha minus x is equal to x plus alpha minus z, which implies x is equal to z. And so we've proved that this is then alpha minus x, this is x, Now, because this is alpha minus x, and this is x, that means this is alpha, and then this is 90, and f lies on this circle that we needed to lie on. And that finishes up the problem. It's a trigonometric heavy problem, and it uses this this point f. You might see in other problems. You might have seen if you saw one of my Canadian Math Olympiad videos. And it's a somewhat common point that appears. This is the midpoint where the Similarity line intersects the circumcircle of ABC, and then the midpoint of A and that line. That's F. And you can also see it's the midpoint because OFA is 90. Now this finishes up our problem, and as always, thanks for problem solving.